Hello everyone, I am Aslı Alpman and I am going to present my Foundations of Magnetic Resonance Imaging term project. In this project, I investigated the FID signal in presence of the off-resonance sources. To do this, I used the signal equation derived as follows. The magnetization vectors press around the main magnetic field and it creates a change in magnetic flux in the receiver coil, and this change induce electromotive force due to Faraday's law of induction, and if we integrate this electromotive force over the volume, we can obtain the received signal. And this electromotive force can be written as dot product of the magnetization vector and magnetic field due to principle of reciprocity. This magnetic field means that the magnetic field created at that specific location due to unit current in the receiver coil. And in our context, it is the coil sensitivity, and I will assume that coil sensitivity is uniform, and I can take this out of integral. Also, I will assume that receiver coil is in transverse direction, so I will use transverse magnetization. Transverse magnetization experiences a phase due to main magnetic field and inhomogeneity and gradient field. Also, it experiences the T2 decay, and if we take derivative, we will obtain the law equation, and in this equation we can ignore the phase due to inhomogeneity and gradient field, since the main magnetic field contribution is much more higher, and results equation is the above one. But since this is a constant, we can ignore it, and in most of our analysis we already ignore it, and I will also ignore it, since my aim is to compare FID signal between each other. And in simulations, I represent magnetization as a vector in a complex plane. I assume that coil is placed in the x direction and has uniform coil sensitivity over the object, and main magnetic field is 3 Tesla. Lastly, I assume that object of interest is homogeneous. And results in first plot, FID signal only experiences T2 decay, and as you see, the envelope of the signal is coherent with the exponential decay with T2. In second plot, I introduce inhomogeneity from a random variable, Gaussian random variable with 1 kHz standard deviation, and as you see, decay is faster than T2. It is because phase distortion within the voxel. Since every spin experiences different phase, the coherence fastly disappears and signal decay faster. And this new time constant is smaller than T2, which corresponds to T2 star. And this is the resulted spin magnetization distribution. As you see, the red magnetization vector, all of them has different phases due to random distribution. Also, I use more stronger inhomogeneity from Gaussian random variable with 10 kHz standard deviation. As you see, decays become faster. T2 star becomes smaller. Also, I use gradient field, and this gradient field, as you see, the 0 point does not experience any phase, but as you go further in x direction and y direction, phase gained in left-hand side rotation increases. And the FID signal resulted is shown in first plot. In here, I did not introduce any inhomogeneity. We only have gradient field and T2 decay. As you see, the signal has sink-like shape, and it has peaks periodically. I think it is due to when I introduce a gradient field, after a while the spins align with each other and it creates a peak, but this peak is not stronger as in the start, since it experiences a T2 decay. But when I introduce a strong inhomogeneity, I did not observe any peak like that, since alignment becomes harder and it takes more time, but until this alignment, T2 decay already destroy the signal. Also, I simulate FID signal with different slide thicknesses. In blue one, slide thickness is quadrupled, but when I scale it, I see the same shape. So I did not, in non-scaled version we can say that it has quicker decay, but in scaled version they were the same. So it does not correlate with the FID signal in scaled version. As conclusion, we observe that inhomogeneity, gradient field, and slice thickness affect the FID signal.